Well, okay, our first paper is EnclaveDB A Secure Database using SGX. The presenter is Kapil from Microsoft Research. Let's welcome our speaker.
Thank you. So my name is Kapil Vaswani. Hello and welcome. My talk today is going to be about EnclaveDB, which is a secure database that's fully functional, offers full SQL functionality, has strong security properties, and has been designed specifically using SGX enclaves. This is joint work with Christian Prieb from University College of London and my colleague Menel Costa from Microsoft Research. So before I talk about EnclaveDB, let me first describe what we mean by a database being secure. What does security mean in the context of a database? So we believe that a secure database should offer the following security guarantees. So we expect the database to protect all sensitive data and provide confidentiality for both queries and for data. And this is important because there are a large number of applications where the queries, for applications like high-frequency trading, where the queries are probably more sensitive, if not equally as sensitive as the data itself. We expect the database to protect data and queries from hackers who might have compromised the system and have privileged access. But we also expect the database to protect the data from database admins and server administrators, and this is increasingly important in a cloud-like environment where these tasks, like a database admin task, is being increasingly outsourced to third parties who we may not want to trust. And to defend against attacks like insider attacks, we also want the database to support advanced security features like online rotation and revocation of encryption keys. But beyond confidentiality, we'd also expect our databases to give us integrity and freshness. And this is extremely important in applications like online voting and online auctions. And what we mean by integrity and freshness is that we expect the transactions we submit to a database to obey the SQL semantics. And also we expect the transactions to execute in an order that respects the consistency properties that the database promises. For example, serializability. And we also expect the database to never lose transactions, and that's why we want the database to guarantee freshness. We also want the database to have a small trusted computing base, full SQL functionality, and good performance. And as far as we know, none of the previous database solutions offer all of these properties. For example, encrypted databases offer some form of confidentiality, but don't offer integrity and freshness, and don't offer full SQL functionality. So here's the outline of my talk. I'll first describe EnclaveDB and its architecture, and I'll describe some of the core design decisions that help us get these strong security properties. I'll describe the transaction API that the database exposes, and I'll talk about a key component of EnclaveDB, which is a high-performance protocol for ensuring the integrity and freshness of the checkpoint and the database transaction log. And finally, I'll present a quick evaluation of the system and finish by some conclusions. So what does EnclaveDB look like? So in EnclaveDB, the database is composed of server-side and client-side components. On the server side, we have an untrusted SQL Server instance, database instance, that is responsible for managing and running queries on all public data. But this SQL Server instance is going to create an enclave. It's modified to create an enclave and host all sensitive data inside the enclave, along with an in-memory query engine that's responsible for processing queries on sensitive data. The in-memory query engine also has a transaction manager that's responsible for serializing, for doing concurrency control and serializing these transactions. The whole server uses a shared log, a database log, for serializing transactions and persisting them for recovering from failures. The whole logging component in EnclaveDB is completely untrusted. On the client side, we have a key management service where users who create an EnclaveDB instance upload their encryption keys with a policy that defines the exact enclaves that the keys can be released to. And these are keys that will be used to encrypt transactions on sensitive data in the database log. EnclaveDB defines a new mechanism for writing queries against sensitive data. So we expect that the queries be compiled and optimized on the client side and compiled into native code. And these binaries are then packaged along with the in-memory query engine and deployed on the server inside the enclave. And that way you get, when the enclave is set up, you get a measurement that includes all the queries that you're going to run on the database. And finally, clients that want to connect to the enclave, connect to the database and query sensitive data, connect to the database using a client library that sets up a secure channel with the enclave. The library is also responsible for encrypting all parameter values that are passed in the query to the server, and decrypting all the result sets and passing them back to the client application in clear text. So this is an architecture that gives us some very interesting properties. So we chose an in-memory query engine specifically because it aligns well with the nature of enclaves. It guarantees that there are no explicit information leaks when we perform operations on in-memory tables, because all the operations such as indexing are performed in enclave memory, and there are no explicit leaks there. The choice of using native compilation to compile queries upfront on the client side reduces the attack surface of the server running of the code running on the untrusted server, and allows us to guarantee to end users the exact set of queries that the database will process on sensitive data. One of the other reasons we chose SQL's in-memory engine is because it has very few and very well-defined dependencies on SQL Server, on the operating system, and on the CRT. So it's very easy to port inside enclaves. And it has a relatively small TCB compared to the whole SQL Server, which is 10 million lines of code. The TCB of the in-memory query engine and the transaction manager is relatively small. The other reason why we chose an in-memory query engine and this architecture is because it lends to a very simple programming model. Unlike encrypted databases where you have to explicitly choose individual columns and decide to encrypt them, here you just simply decide the set of tables that contain sensitive data and host them inside an enclave. We do, in our architecture, assume the support for very large enclaves because we are going to host all sensitive data and the indexes on this data inside the enclave. These large enclaves don't exist today, but we believe there is no real reason why enclaves should not expand and support large amounts of memory. So let's go a little bit deeper and look at some of the interfaces of EnclaveDB between the untrusted and trusted components. So in EnclaveDB, the SQL Server uses a transaction API to invoke transactions on sensitive data. And in turn, the enclave uses the untrusted server, SQL Server instance, to log transactions to disk and to create checkpoints. So let's look at some of these APIs in more detail. The transaction API that EnclaveDB exposes is very simple. There is a function called txalloc that you use to allocate a new transaction that assigns the transactions a new logical timestamp. And then you call txexecute to load a pre-existing stored procedure binary that has already been deployed inside the enclave and run the transaction. txexecute will automatically authenticate parameters using a key that is set up during the creation of a secure channel with the client. It executes the stored procedure entirely within the content within enclave memory and writes encrypted results back to the buffers that are then passed to the user. Once a transaction has executed some code, the client is expected to call txprepare to try and commit this transaction. The commit is in two phases. First, you prepare the transaction commit and then do the actual commit. The prepare phase checks for conflicts, and if there are no more conflicts, it assigns the transaction an end timestamp, a logical timestamp, and then waits for all dependent transactions to finish, and then initiates log IO. And this is a phase where we encrypt the log IO to disk to ensure that the state of the log doesn't leak secrets. And finally, you can call txcommit to notify all dependent transactions and release all resources, or call abort to abort the transaction. So we've hardened this API to protect against a variety of attacks that include attacks that, for example, time of check and time of use attacks, and API misuse attacks that for example, try and commit a transaction that is previously, try and abort a transaction that is previously committed. A core part of this protocol is the log, because the log is the logging component in EnclaveDB is completely untrusted. So the logging is completely managed by the host. The host exposes, again, a simple API for logging. The enclave can call the host to append a transaction to the log, and that the append API is completely asynchronous. So the enclave will pass to the host a transaction handle along with the size, the expected size of the log record. And when the host allocates size in the log, it calls back into the enclave, and in the callback passing a pointer into the buffer where the enclave can write the transaction log. The log also supports truncation for checkpointing, so you can truncate the log at some point, and after you've written the state of the truncated log into a checkpoint file. Notice here that the logging is completely asynchronous. It's callback based, and the log supports concurrent append. So there can be many threads inside the enclave that are concurrently writing to this log. And how does checkpointing work? Well, at some point when the enclave decides that the log has grown long enough, then it can decide to checkpoint. The checkpointing process reads the transaction write sets and writes them to a set of data and delta files. The names of all of these files are written to something called a root file, which is a list of all the checkpoints that the database has created. Now, protecting the integrity of the log and the checkpointing process is very important, because this is what gives us all our security guarantees. Protecting the state of the checkpoints is relatively straightforward. We can simply encrypt all the checkpoint files and bind the root file to a monotonic counter so that the adversary cannot replace the root file with a previous version of the root file, and in the process, we lose checkpoints. And this process of binding the checkpoint file to a root file can be achieved using a protocol called Adriane that was proposed in Usenix 2016. And the idea here is that when we write the file, when we write the root file, we encrypt the root file, and in the root file embed the value of the current counter value, and then increment the counter after the file has been written out. And the problem with this scheme, with incrementing the counter after writing the file, is that if there's a failure after the file has been written, then the adversary has a copy of the file which corresponds to the next version of the state, but the counter hasn't been incremented. And the adversary can use that next value of the next version of the file to fork the database at some point later. And to prevent these attacks, the read file process from within an enclave does the following. It reads the current counter value and asserts that the file you are getting corresponds to the current counter value, but then it writes the file and binds it it increments the counter twice, and each time writes the file out. And that invalidates all the forked version of the file that the adversary might have had. So there's a simple scheme for ensuring that we can protect the checkpoints from being the adversary from replacing the checkpoint root file and then rolling the state of the database back. But ensuring the state continuity for the transaction log is a lot more challenging. And that's because, like I mentioned, the log is being updated incrementally. So the log is not a whole blob of state that you can keep writing out every time you update it. The log is being appended to, and the logging API supports both concurrent appends, and it's asynchronous for high performance, and it's also being truncated. So to guarantee that the log is the latest log, when you recover the log is the latest, is actually quite challenging. We considered using a Merkle tree, the combination of a Merkle tree and a monotonic counter for ensuring state continuity for the log, but that unfortunately introduces a single synchronization bottleneck in the whole system, specifically on the root value of the Merkle tree. And that's why that's the reason we propose a new scheme for ensuring state continuity of the log. And this relies on some key observations that hold in the context of a database, specifically an in-memory engine. And these observations are as follows. In a database like ours, it turns out that enough for us to recover when a failure occurs. It's enough for the database to recover with the set of log records that have committed but have not previously been truncated from the log. More specifically, the order of the log records in the log doesn't really matter. So we don't have to ensure that when we read the log, we recover the log records in exactly the same order, because the order is based on a logical timestamp that the database engine has assigned and embedded in the log record. And the second observation is that any transactions that are in flight when a failure occurred, for example, transactions for which log IO has been initiated, but the host hasn't acknowledged that the transactions have been written to disk, it's OK to discard those transactions from the log, because we haven't really notified the users that these transactions have committed anyway. So it's OK to discard those transactions for which IO has been initiated, but we haven't committed to the user. So based on these very key observations, we have a new protocol that ensures the integrity of the log. And this is based on tracking sets of log records using vector clocks. So let me quickly describe this protocol. So this protocol uses monotonic counters. There is 3 sets of monotonic counters per thread. So here I'm showing on the x-axis is time and log records. There are 3 sets of counters. There is a counter that tracks all log records that have been truncated per thread, and a counter that tracks the set of committed log records, and a counter that tracks the set of uncommitted log records. The set of the committed log record counter per thread is incremented before a thread initiates log IO for a transaction. And the uncommitted log record counter is incremented before a thread initiates log IO. The committed log IO counter is incremented after the host notifies the enclave that a transaction is committed. And the truncated log record counter is incremented when we checkpoint. So what this tells you is that if you look at the 2 vector clocks, the committed and all vector clocks, the difference between them tells us the set of log records for which we have initiated log IO, but we haven't yet committed. Each of the log records is also encrypted and timestamped with these counters, stamped with these counter values. So each log record is unique because it identifies the thread that initiated the log IO and the counter value. And during recovery, we ensure that we can recover only if at least all the committed log records are available. So we don't expect all the uncommitted ones to be there, but at the very least, we expect that all committed log records must exist in the log. We also have a scheme for invalidating all the log records that were uncommitted so that an adversary cannot reuse them and launch attacks by reusing previously uncommitted log records in later executions. But again, I'll skip this for the lack of time. A quick note on the implementation of monotonic counters. SGX does support monotonic counters, and these are counters implemented in the management engine. But these counters turn out to be too slow, especially for the kinds of throughputs that we expect. So each counter update in SGX is roughly 100 milliseconds, and that's very, very slow. And these counters are also not useful across when we migrate a database instance across servers. And therefore, we use counters using replicated enclaves. These guarantee availability as long as a majority of the enclaves are live. And we also use sharding to improve to get higher performance. So let me quickly describe the evaluation. So we evaluated our design using a very high-end server configuration. So we have 4 sockets, 32 cores, 512 gigabytes of memory, and a disk that is striped 8 ways, 256 gigabytes each. We have 2 benchmarks, 2 standard database benchmarks, TPCC and TATP. And in both of these benchmarks, we assume that all the tables and all the stored procedures are sensitive. We assume that we have very large enclaves. In our case, we assume that we have enclaves of size 192 gigabytes. Since enclaves of these sizes don't exist yet, we had to use a performance model to estimate the performance. And we validated the performance model using existing enclaves, using existing SGX enclaves. And the details of the performance model and the validation are in the paper. Just to quickly describe the performance we get. So the result on the left, the graph on the left shows you the performance for throughput for TPCC. There are 4 configurations: baseline, Crypt, which represents the configuration where we enable encryption of log records and parameter values. Crypt call, which also simulates the overhead of calling in and out of the enclave. And crypt call mem, which also stimulates the overhead of memory encryption that SGX imposes. What we find here is that the overheads of our system are reasonably low, especially for the kind of security guarantees we get. So it's 40% in the case of TPCC, 15% in the case of TATP, and the difference is because TPCC is a more write-intensive workload, whereas TATP is a more read-intensive workload. And the reason why we get low encryption overheads are because our encryption and decryption is at a coarse granularity. We are encrypting and decrypting log records, not individual values. And we've done a whole bunch of optimizations to ensure that we have no bottlenecks on the critical path. So just to summarize, EnclaveDB is a database designed for high security. It achieves security with good performance and a reasonably small TCB. And a core component this is a new protocol for ensuring integrity and confidentiality of the log and the checkpointing process. As described in the paper, EnclaveDB enables new scenarios for a database to be used, for example, in a setting where you have multiple users who don't trust each other and want to share a single SQL database instance. There are a large number of open problems here. For example, transactions that span public and private data, of course, side channels, and reducing the TCB even further. Thank you, and I'm happy to take some questions.
We can make time for one question. Please state your name and affiliation, please.
Raluca Popa, UC Berkeley. Very nice work. I really enjoyed it.
Thank you.
So you do a bunch of work on integrity of the logging with concurrencies, and that's a really neat technique. But I wonder what happens to the actual data records. You probably have a similar issue. So I imagine that for integrity, you use maybe a Merkle tree, either built into SGX or your own. But concurrency with that is difficult. And isn't that becoming a bottleneck?
So for data records themselves, we assume that we have all the sensitive data is in enclave memory. So we rely on hardware to protect the integrity of all sensitive data and indexes on those data.
I see, because the hardware itself is essentially implementing a Merkle tree of some sort, and that
yes, it
itself has concurrency bottlenecks. And
yes.
I wonder if you haven't run into that as a performance issue.
Yeah, so we have modeled that in our performance model as much as we can. So that our performance model includes the cost of integrity, of the additional cost of integrity on memory accesses.
I see. It might be worth looking at the real hardware for that, because we run into a bottleneck in a
yes,
situation.
yes, of course, yeah.
Okay, thank you very much. Let's thank the speaker.
Thank you.
Yeah.